Thank you everybody for having me back one last time here on the stage. So we're gonna, 20 minutes here, we're gonna make it exciting. We're gonna dig into some of the things that we could be doing with customer innovation to really drive value in the utility space. So this is not gonna be so much about communications. We're gonna talk more about the grid. Why? We keep saying we need reliable, cost-effective power. And we keep talking about all these demands that are impacting the grid. I want to dig into the technical side, the utility operations side of what does that mean, and then tie it back to, we'll talk about three aspects of this, and tie it back to what does that mean for what are we doing here at UBBA, and kind of give us a challenge statement for things that we need to be looking at tomorrow in PlugFest as we work in the industry over the next couple of years. So we've been talking about how do we get reliable, cost-effective power, and there's a fundamental shift that I believe is going on in the grid right now, which is in all of our history, we've always built the grid to supply the demand that was occurring at any given point in time. We invested to build the plants and the wires and the transformers for whatever we all wanted to consume. And we don't think about it when we turn the switch on, is that light gonna come on? We expect that capacity to be there. But in this time where we have a lot of new supplies of energy coming on the grid, we have more distributed assets, and we have expanding demand for the use of electricity, we don't necessarily want to see our price of electricity skyrocket as we keep investing more and more into the infrastructure to make that happen. We will have to keep investing for sure, but we're also at a situation where the most efficient thing to do to keep our costs as cost-effective as possible is to continue to match our load to the available supply. With renewables, we have some intermittency to their capacity. We could, as the grid scale, store all of that excess energy that we need to in grid scale storage and then dispatch it into the grid when you want to consume it as a consumer. Or more efficiently, we could align your consumption to the available supply because we have several ways of storing energy through how we choose in consuming it. Most directly is probably electric vehicles, but also the heating and cooling of our properties, the production of hot water. There are many things that we are adding to the electrical grid because it's one of only two mechanisms we have to move energy in a carbon-free way. And we see lots of demands, and then you go add that whole AI data center thing to the transmission system at the site. That's a whole other demand unto its own. While we also have the challenge of addressing where is the capital investment gonna come from? We are seeing, as we consult with our utility clients, more and more demand for those capital dollars. When we talk about doing reliability projects, clients are coming and saying, you know, we used to have X amount of money for reliability and we used to spend Y on customer-driven projects. Those are interconnect projects. Those are projects that we have to do as a regulatory mandate to accept that new load onto the grid. And to increase load on the overall system, we want to interconnect that capacity. But that required customer interconnect capacity keeps creeping up and starving those reliability budgets for a little bit of the capacity that they need to invest. And with all of the transmission scale deployments that we need to do, everything that we need to do to build generation to generate the supply, we want to try to do everything we can to get every ounce of efficiency out of those existing assets. So let's explore a little bit what's been going on at a customer level. It used to be that we had a home and you might have been 3 or 4 kilowatts worth of electrical load and you might have bought 30 to 50 to 60 kilowatt hours per day of electricity. You had 1 or 2 EV chargers. Each EV charger for a typical level 2 charger is 9 kilowatts. Just by adding an EV to your house, you doubled the coincident load for your property. If you had 2 of those, you doubled again. If you think about the transformer that's supplying your house, you think, I have a 200 amp electrical service. How big do you think the transformer that's supplying that is rated for? It's rated for 200 amps. How many customers do we typically have connected to one of those transformers? 2, 3, maxes out usually 6, sometimes more. If we are not making efficient use of when we choose to charge these assets, we're gonna have to replace that transformer. We have to upgrade that wire. When we do, we're spending capital dollars for marginal increased capacity of kilowatt hours sold. If we can spread that load out evenly over time, we can use the existing infrastructure we have close to the consumer. We might have to make transmission upgrades to make those assets better connected. And it keeps going. If we convert heating, you're now running effectively your air conditioner as a heat pump all year round. How many hours does a typical heat pump run to heat your home on a cold winter night? It runs more than what it would take to air condition your house during the day. It has to run more intensely. It has to run for a longer period of time. You add that load to domestic hot water heating, and you now are starting to require upgrades of electrical panels, distribution feeders, distribution transformers, and we don't want to invest in that unless we absolutely have to. So how does that come back to our private LTE space, and what are we working on here? We can consider non-wires alternatives to upgrading these assets, but it requires we have information about what is going on in real time with these assets, and what are we doing to spread out that load over time. So I'll ask you as audience question here, how do we convince consumers to operate their load at the point when the grid can most accept it? Do we send them text messages? Do you guys all want to adjust your load profile based off of communication? Generally, no, we just want it to work without us being involved. Anybody have any other ideas? Have you ever heard of this thing, time of use rates? Time of use rates are all about creating the incentives to get us to shed our demand into times when the grid has the most capacity. How many of you are on time of use rates today? See a few hands. I definitely don't see a majority. Can't see very much up here, quite frankly, at all, but they're just starting to roll out. And most of the time you have a peak rate, an off-peak rate, you might have a super off-peak rate. I don't think that's gonna stay very static. I think we're gonna move into a day and age when we're gonna have lots of more dynamic rates adjusted for individual purposes. For every one of these electrical consumption profiles, I could see us having different rate structures to incentivize very specific aspects of electrical consumption at a given point in time. Does everybody remember free nights and weekends for our cell phone plans? Certain parts of the country, did you know that you can get free nights and weekends for electricity? If you live in Texas, in the deregulated market where you can directly choose your energy service providers, there are service providers that will offer you free nights and weekends. That's for general electrical consumption. I don't know how much free nights and weekends will be maintained, but I very much expect that we have a situation where it says, if you charge your EV during these times, and I eventually think we'll move away from these times to when the grid has capacity, we'll offer you a lower rate for EV charging. For domestic hot water heating, we have a lot of flexibility when in the day we heat domestic hot water, because most of us have a large tank that can store that water for an extended period of time. Your hot water heater usually only runs probably when you take a shower, and the rest of the time it's just sitting there with stored energy in it. We have a lot of flexibility about when that occurs, and if we have a specific challenge on the grid, we can move that around. How is that communication and how are those rate plans gonna work? And I think that hits at the core of what UBBA is working on and what we need to be considering. And that is, how do we build the infrastructure and the platforms, both the communication so that we can get real-time information about what's going on in the grid, and provide real-time information about what we should be doing from a consumption profile. And here we're talking about just one scenario, just one use case of what's going on in your individual home. And we know that this is already taking effect. If you buy an EV today, and especially if you get two, and you only have a 100-amp electrical service, you can't charge them, run the oven, the air conditioner, the hot water heater, have your internet router and your TV and your lights all on at the same time. You will trip your main circuit breaker, and it's there to protect you from overheating your electrical service conductors. Instead of just adding that load, you can add real-time control. You can buy a smart electrical panel, a smart EV charger that'll monitor and say, oh, if I see that you're using your oven, I will only charge your car right now at 4 kilowatts instead of 9 kilowatts. Or if I see both EVs are charging, I'm gonna charge at half the rate. And that upgrade might only cost you a couple of $1,000s for a smart electrical panel or a smart EV charger versus maybe spending $4,000 or $5,000, $10,000, $15,000 to replace that equipment. Now, if you take those same ideas and you apply that at grid scale, where a major distribution power transformer, multi-MVA transformer might cost millions of dollars, upgrading lines can cost $1 million per mile, these numbers start to become very significant and are the key under which we need to be advancing the grid so that we're not raising prices faster than we have to. But to do that, we have to have reliable communications and, I will contend, new AMI meters that are capable of understanding what's going on in your electrical load so that we can either monitor what has occurred and charge you appropriately for the rate structure, or communicate with you so that your device chooses to consume electricity appropriately. How I think I don't want to have to tell my dishwasher, can it run or not run right now? Is it on peak or off-peak or super off-peak rates? What I think will happen is when you deploy your refrigerator, your dishwasher, you're gonna, on a touchscreen, pick, I want lowest cost of electricity, or I want absolute run, whenever I hit the button, do exactly what I say right then. And there's gonna be a cost difference for doing that. And those devices will go out and check our APIs that our distributed energy resource management systems publish and say, this is how much capacity at your home right now, today, is available to you, and this is what your real-time cost of electricity would be, and do you want to run right now? And if it's maybe your dishwasher's example, you hit start, you go to bed, and it actually runs at 4 in the morning when we have excess capacity. That is a much more cost-effective way of adding capacity to our grid. And it's very efficient for the utility, because now we're taking the same fixed amount of assets and getting more kilowatt hours delivered. If everybody understands your basic utility rate equation, cost of capital spent divided by kilowatt hours delivered, such your revenue requirement. If we can increase that capacity, we can maintain our rates and make the capital investments that we need to be making. But then we get into this question, if we're doing non-wires alternatives, and this is where I think the most exciting things for UBBA comes in, if we're doing non-wires alternatives, how reliable does that infrastructure have to be when we decide not to invest in the physical infrastructure? We now depend on communicating these messages. We depend on that load spreading functions to occur to be able to have reliable electrical service. And that, I think, is the underpinning of why we're building these private networks. Now let's explore that a little more, because one of the challenges that I see is these assets are not, in many cases, utility-owned assets. The things that we're wanting to influence about how they consume are customer-owned, i.e. probably not directly controlled by utility systems, instead influenced through predominantly those rate structures. We already heard examples today where if we have a electrical system upgrade that's being planned, we could consider deploying batteries in customers' homes as an alternative, and that is more cost effective than upgrading that asset. We might defer that upgrade out 4 or 5 years, or maybe indefinitely, that we can take better utilization of distributed production into the system, but we have to coordinate that, and we need some form of direct communication. I don't know what the right answer to this is. I don't know how we get reliable communication to those grid assets. Let's talk a little bit about what we actually have to communicate to them. If I have a smart inverter with solar panels on my house and it needs to interconnect with the system, it gets most of the information it needs to be interconnected from the electrical grid itself. It gets the frequency, it gets the voltage, it matches those. If you want to put power into it, will slightly advance the phase angle and you can push power into the power grid from your smart inverter. And that's great when you have a 5 kilowatt inverter pushing against a grid and it happens to have a gigawatt scale spinning generator in it that has a lot of mechanical inertia, weighs thousands of tons, it's spinning at 60 hertz. If there's a disturbance in the system, the inertia that comes from that large spinning machine will balance out what's going on the grid. As we get more and more distributed assets, they're trying to follow the grid around. And when they're following the grid around, they start to hunt. And sometimes they don't work so well. They actually are challenging the stability of the grid right now because we don't know how they're all going to respond. With private LTE, we can make the problem fundamentally better because with power electronics, we could ask each one of those to hold frequency at their location, and instead of bailing off the grid and saying, the frequency's going a little awry, I don't know what to do, and I'm gonna disconnect, we can say, no, please stay there, please put energy into the grid, please hold the frequency at that given location, and add stability to our power system to make it inherently more stable. But there's one big missing component for that. How do you know what the phase of the system needs to be at that given location at that time? Ideally, we could communicate it through some sort of communications network. We have the ability to do that over fiber. Do we have the ability to do that over private LTE? I don't know. We have the protocol. Precision time protocol allows us to do it. Does it work at the scale and the reliability that we need? Would we be willing to improve the reliability of the system through those private assets? We still have to tie it back to that conversation of how do we get that connectivity, though, to an asset that we don't necessarily control. And I think that's something that we need to explore in some of our working groups. We need to explore as we are interconnecting new devices into the system, and that we fundamentally need to be answering. So we've talked about how can we keep rates down by making more efficient use of electricity at your home. We've talked about how can we make more efficient use of the stability of the grid through frequency stability, again, a communication-enabled asset. Now let's talk about what can we do at the transmission scale. As we think about how we use those assets efficiently, today we provide ratings for transmission assets, typically 2 ratings per year, a summer rating and a winter rating. We look at how much it's rated for. Hey, that wire can carry 2,000 amps under these typical temperatures, these wind speeds, these solar radiation values. FERC came out and said, hey, we think that you can do more and you can get more through your assets because nobody wants new transmission lines in their backyard, and we need to try to do everything that we can to use the assets that we already have. And by adding strictly weather data to that, we're now, next year, going to have to provide ratings for those assets for every hour of every day going forward. So you have to provide a 10-day forecast of what is the capacity. We're seeing with some of these changes that you can get sometimes 10, 20, 40%, in some rare cases even 100% more capacity through that given asset without replacing it. It's not all the time. You know, if it's a cold, rainy night, there's a new data center that wants to consume a lot of electricity, it can get way more energy through that existing aluminum wire transformer than it could on a hot, sunny day. But when we're doing that, we now are doing that based off of models and estimates. If we can put actual sensors out there, put feedback loops in, be able to communicate to those assets, we can do that in real time. When we can do that in real time, we can now operate those assets more efficiently. Next scenario is I heard it mentioned earlier about protection settings. Today, we set the protection settings in the distribution system traditionally assuming one-way power flow and some general parameters of what we expect the load on that system to be. But there are times where distribution feeders are flipping to be net electrical collection buses for solar. If it's the middle of the day, the load is relatively low, we haven't picked up a lot of air conditioning yet, the power flow might be reversing in that distribution feeder, and we are completely not set up for the right protection settings. It's actually a hazard. If there was a fault to occur, we could suck energy from the grid and take all the energy from those solar power sources into the load at the exact same time. We would melt assets. It becomes a safety hazard because we are not clearing that fault quickly on the system, so we're melting something down or wires falling down. Utility workers are at more risk. We need to be able to update those settings in real time, and there's a whole lot of work that needs to be done. Who here has ever changed protection settings on a utility asset? Is that something we do on the fly without retesting it and getting comfortable with the idea of doing it continuously? Traditionally, it's not. So we have to build back-end systems. We have to build real-time models. We keep talking about edge compute and what can we do with edge compute. How do we take a segment of the power grid and give a controller that's running at a pole or at a substation or even a meter on the side of a customer's house the ability to do voltage control locally within your segment of the electrical system, maybe A1 or 2, maybe a bus of a distribution feeder? That is a very complicated problem. We gotta have communication flows from multiple sensors going back and forth. We need real-time, low latency to communication to happen. We're building the applications to make that happen. We're building the infrastructure to make those applications happen today. But are we testing the applications? Are we getting comfortable for the deployments? Do we know how to do the cybersecurity deployment to say the devices that are gonna communicate with each other are gonna change in real time based on real-time load conditions for distributed energy? I don't think we know how to do that. I think these are the challenges that we have today that we need to be investigating and exploring as part of UBBA. I also think we need to be looking at how quickly we're getting devices connected to the grid. I have a little bit of a challenge for all of us in that we've built multiple awesome networks out there. We have a relatively small number of connected assets on that infrastructure being deployed and put into service today. If we want our consumers or the regulators or our T&D friends or ourselves to be demanded to build more of these communication networks, we have to be effective at getting the devices online as quickly as possible, because it's only once we get a device connected and it starts providing value to the grid that we get into the operating scenario where we've delivered on the value promise that we've expected. And when those constituents are receiving that value, that they're ultimately coming back and saying, when can we get more of that? How can we solve this problem differently? Instead of, again, building more or deploying something, we want them beating our doors down saying, we want our devices deployed. The vision and desire that I have is that we can go to a show like DistribuTech, see some application, come back, build the use case for it, want to deploy it on our system, and we don't have to think about the communications infrastructure that gets involved in that. We can simply say, does it have private LTE? Does it support our frequency band? Can we test a few in the lab to make sure that it's certified on our network? And if so, go forth and deploy at scale. And today, we're seeing that we are moving through spectrum acquisition, business planning, getting the RAN infrastructure built out, and then we're spending quite a bit of time as it takes us to develop and deploy the individual assets. And it's because it's a challenge. We've got a lot of parties that we have to work with within our utilities. So can we accelerate the speed by which we are going to be connecting with our T&D friends, the energy operations centers to be able to deploy these assets and provision them, the warehouse to deploy, how do we get SIM cards into hundreds of thousands of meters if they're going to be deployed by the semi-load? These are the problems that I think are here today, are upcoming. These are the things that we're going to be showing you some of tomorrow in PlugFest, how we can address. These are the things that we're working on in our user working groups, where we're coming together in an industry, talking about how we can solve these problems. And these are the things that when we get deployed effectively on our infrastructure, we have the ability to accelerate the deployment of these networks throughout the country. We're even talking internationally now to our business partners in other parts of the world of what is their capacity and what is their interest. And that's ultimately what I see accelerating our work here at UBBA. I want to say thanks for all of the hard work that is going into this, and I hope you have learned in this conversation a little bit more about how is it that we enumerate the idea of what does it mean to provide safe and reliable power? What are we talking about when we're talking about connecting these distributed assets through some of the stories that I've told that help you understand these are the things that we need to create, develop, build as an industry to have success in deployment going forward. So if you have questions for me, I'd be happy to answer them probably off to the stage at a later time because I believe it is now almost 5:18 and time here in a few. I guess, do we have to wait till 6 o'clock to go to the party? So I guess we get more time to chat in the lobby, go put our bags up, and have a wonderful rest of our evening. I cannot wait to see everybody next door for our opening reception, and I would love to talk to you more about some of the ideas that I've shared here today. So with that, I will say thank you. And Bobby, is there anything else you need to say? Bobby says, let's go party. So thank you guys.